Yeah, I really like our RU program because it brings in a lot of students and diversity into the program. So I think it's been successful. So, all right. So our last speaker this afternoon is Dr. Bruno Basso. So Bruno is from Michigan State University. He's the John Hanna Distinguished Professor in the, I got to look it up because it's changed again now, Plant, Soil, and Microbial Sciences. When it was just plant and soil. They added microbes since I've been there 30 years ago. But Bruno and I we've worked together quite a bit. He serves on the National Academy of Sciences Board on Ag and Natural Resources, which I chaired up until December but we've had interactions before that and interactions now as well. So Bruno, I don't know if I sent the publication around, but Bruno's quite diverse. He's really looking at developing and applying advanced crop system models to predict the impact of weather, soil management systems on short-term and long-term yields, nutrient uptake, water usage efficiency, and environmental outcomes. His second approach is to advance the limitations of different air and spaceborne platforms to obtain remotely sensed data and link this information with algorithms to understand spatial and temporal nutrient and water uptake by plants and to integrate this information into quantitative models. And thirdly, assessing the impact of climate variability and change on agricultural production systems. And so, Bruno, we've talked a lot this afternoon about the weather variability in the Southern Great Plains being super dry to, in parts of Oklahoma, saturated. So all in one season or half year or so. So anyway, the reason I asked Bruno to talk was, again, I want us to think a little bit out of the box and forward thinking on potential next steps, grants, and that. Bruno, as well as Jerry and myself, are filed a couple projects. One is this carbon negative agriculture research endeavor that's under review by the National Academy as well. And then Bruno wrote a couple of, I guess one was in PNAS, and I forgot the other article, but a couple on precision conservation, and the other is on regenerative ag practices and using technology to advance regenerative ag. And I know that's a current hot topic right now in that. So Bruno, I won't take away your time. Bruno's in Italy right now, I assume, right? I think you said it was 11:30 there?
11:35, yes, but no problem. I'm at night now.
All right. So I really appreciate Bruno taking his time away, his evening away, and spending an hour or so with us, about 40 minutes, 45 minutes, but then, or I think 40 minutes or so, but then ask lots of questions. So with that, Bruno, I'll turn it over to you.
That's great. I'll share the screen. Hopefully you can see it okay.
Yeah, we got it.
Okay, great. Well, first of all, I'd like to thank Chuck for the invitation. As he mentioned, he and I have been working quite a bit together over the last few years, both on the banner committee at the National Academies and other different interactions. And so it's a pleasure for me to have the opportunity to share some of the latest research that have been doing in this pretty broad, field of using technologies. But the ultimate goal is really trying to change agriculture from, being a problem in the sense of emission to a potential, solution. And so how can we scale these climate smart, practices and be able to, again, revert the role of being affected so heavily by climate change and extreme events and so on. So just briefly, I'm not going to have several. This is the only slides. It's so well known by everyone about the challenges that agricultural faces and food system in general. We have to continue to grow nutritious food, which is important to underline that component. Feed animals, generate energy with less land that we have now in a changing climate. And we need to protect soils. If we don't protect soils, we basically have very little chance of succeeding air quality and biodiversity, which is never basically underlined enough. We need to reach negative greenhouse gas emissions. I always say, plants, which is the basis of agriculture, pull CO2 for living. And so it's a paradox that we manage to have emissions from agriculture. So despite the fact that we pull CO2, we still have greater amount back into the atmosphere the way we manage our land and our system and our animals. And it is just of paramount importance that we need to understand that every time we give a suggestion and to a farmer, we always risk neutral. We don't bear the risk that they have. And so we need to make sure that, we provide this reliable revenue stream to farmers. And again, to de-risk some of the technologies, and so incentivize the very much needed change. And so you see some of the photos. It's not a surprise to anyone that we lose about 10,000 hectares per day on urbanization on a global scale. Deforestation continues to be a problem because of indirect land use, and unfortunately agriculture is one of the causes. But that's an issue that could easily be changed the way if we catalyze the change that I will also mention through my talk. And then fires, land degradation, also consequences of management and high temperatures, soil erosion. You heard statistics. I mean, in the US, it's roughly close to a pound of soil per bushel of corn produced. And water quality, especially close to where I live, we have significant issues for excessive amount of nutrients not taken up by the plants ending up in water bodies. So the one of the aspects, if you see these bullet points here, which they go under the principle of circularity, and then several other extension around it, circular economy, circular bioeconomy. But if you think about it, it's what we all should aim, to do in our management. We have to increase nitrogen use efficiency, reduce pollution, trying to recycle as much as possible the materials, both residues, organic amendments, regenerate the system and provide economic benefits. So that's basically the definition of a circular system. And in agriculture, in more broad terms, the principle of regenerative agriculture, they're basically listed there, and they're based on these bullet points, which they lead to potentially, a big chunk of circularity. So high diversity in terms of crop rotations. We can't just continue to have corn after corn. And for the very known reason of being able to improving the microbiomes of the soil health, and be able to sequester more carbon. It's well known that diversity of species leads to a greater accrual of soil carbon, independently, even independently by the amount of residues that you may add. So I'll talk more about that. Regenerative nutrients, and in compost, like with biodigestate, now we can use, animal waste into production of biogas and so on. Animal integration, the animals will never go away, should not go away, and it's part of the culture of people, and they should be managed better. And so grazing, forages and residues and a role in generating energy and so on. We need to have cover crops, perennials, agroforestry, and then precision conservation when, Chuck asked was one of the core aspects which I will focus. And it's so important because when farmers see the analysis that we're doing, they're pretty much blown away of their own data. There is not much modeling or other stuff. And you'll see it yourself, how the level of losses that they get by managing areas not, profitable to be growing corn on it. Continuous, minimum tillage, low corn, low or no tillage at all, and the precision technology from planting to variable application. Key ecosystem services, immediately profitability, farmer well-being, greenhouse gas emissions, mitigation, soil carbon sequestration, be able to conserve, biodiversity, pollinators, and soil health. And one of the reasons, people here, obviously, if you grow the same crop over a large areas, it's very much like imagine, an aeroplane not be able to land because no landing strips, no airports. That's the same thing for insects and basically the biodiversity. So soil health and water quality will benefit from the key principle that I showed. And so in general, this is, even though, as you all know, I'm a biophysical scientist, there needs to be a much closer collaboration with social scientists to be able to lead to really one health concept, both because the ecosystems which we work on, improving the health of the ecosystem leads to more nutritious food, and the health of the farmers improves of the people, the communities in general. And so there is a close connection through a system approach. So when I talk, I'm a system scientist, and things, basically analyzed in isolation can never basically solve the problem because they just don't account for the externalities of other things occurring within the system. And so even here and agriculture is made by so many subsystems, the soil, and within the soil, there are subsystems. And so be able to quantify this interaction and the system boundary is important to see how we basically using these resources. How do we flow? We have a very good knowledge of the pathways, how the green arrow carbon flows into the salt plant atmosphere, as well as nitrogen and water. But in order to do that, we have to account for this interaction, and that can only be done again if we use a system. Now, beyond just using what we call, models, there has been a trend, and I'm really, a big chunk of my lab works on digital twins. And so it's not just, running a crop model, it's basically digitizing the entire system. And we define it as the bridge between the physical and the digital world to promote innovation and performance. Basically, as you well accept, we can't just do experiments every single place. We can't do trial and error, even though they've been so critical over the years, and they continue to need to be, focused. But there needs to be a very close connection between how the experiment is done and how even the model is helping designing some of the experiments, such that the knowledge of the system approaches is improved, rather than observational type of studies without understanding, too often the mechanisms that led to their particular sets of outcomes. And so growing plants on the computer, you can run pretty much infinite numbers of what-if scenarios. As long as the models are validated, which they need to be, and require, measured data, then we'll get our chance, basically lined up better. And this is an example of the interaction that occur on a system, on the soil, basically soil water balance, soil heat balance, and nutrients and so on, phenology, and just basically all the possible interaction, both occurring in the plant, in the atmosphere, in the soil are captured. But what is happening also we work with farmers very closely, and they pretty much have a digital twin of their farms. You know, they basically have a cloud-based analytics of everything that gets stored and the data that gets collected. So the amount of data coming from the farm, it's still, you know, in a messy kind of state, because so too often it's basically underused, or, you know, quality becomes an issue. But the technology is there to be able to do basically a digital twin of the entire farm. One important aspect, though, even though I work a lot on technology, I really would like maybe mostly the students to walk out with this message that technology should never be considered as the sole solution in terms of fixing a problem, because first of all, it has to be part of a bigger system. But it is important that we are not basically having these big headlights on our face driven by the technology. And an example that I often bring is we can't just have incremental improvement. For example, and imagine, you know, continuing to grow and irrigate, you know, crops in areas that are limited by water. If we continue to, if we develop new efficient way, we just almost legitimize the problem of saying, okay, well, we're doing so much better that we continue to do, rather than understanding through the system that that crop should not be grown in that particular context. And so the transformational change requires courage in the sense of, you know, you can't just place a patch through the technology and continue to feed the vicious cycle, rather than changing the system altogether. And so that's a parenthesis within technology of criticism, and I'll stop there, because it does bring an incredible amount of wealth of knowledge and information. So everybody has seen and very familiar with yield mapping. This is a corn, you can see 12 years is pretty much 1 year soybeans. But the majority of the year, corn, you'll see the variability, and it is very difficult for a farmer to implement the change. The most common thing for people not being very well equipped or, you know, familiar with technology, for most of the farmers have a short memory. They'll remember, you know, they base potentially a potential variable rate just based on last year's map. So what we did, we looked at how each single, actually this works since I saw Jim Dobrovolsky connected. It was through the first SAS, was called CAP, the water cap that I had funded. And so this technology right here, which has been commercialized, is going around with big investment, and even Vice President Al Gore goes around and talking about it, and so on. So it came through one of Jim's investment as for the rain. So I really wish that you could generate a lot of other positive impacts through your project. And by looking at each single pixel and how different it is from the neighbor versus how different it is over time, the same pixel, we learn what these yield stabilities are. The red zones are pixels that they're never the same. So there is a spatial pattern that changes, not every year. You'll see how often they change in a minute, but there are parts where they're constantly low yielding, medium yielding, and high yielding. Now, if you visualize in a different way, here the mesh net, the red net, shows the unstable zones, but the color that is underneath, it shows what is the predominant behavior. So when you see, you know, the red over the yellow, it is mostly low yielding, but 1 year potentially may have had a good year of rain distribution and gave a higher yield. Whenever you don't see, you know, the mesh net, it's a stable crop, either medium or high yielding or low yielding. And so with this, it's been incredible, but I realized that even though we had a wealth of data because of the project, and farmers wanted to really, they were attracted by what we were doing, and we nearly have 250,000 acres of yield maps. Multiplied by the number of years, is significant. It's in the millions of years altogether, but it's still a small amount of data compared to, whatever the 100 million acres, 90 million acres that we have between corn, mostly, corn or soybeans. And so we moved into using satellite. And what you're seeing here, there are basically 1,200 images on this slide, 1,200 images flipping through. And so these are daily images at 3-meter resolution. There's very little we can't see from above anymore if you go at this level of daily coverages at 3-meter resolutions. And so we can detect practices, we can detect, a lot of this change. And so I used, even though I didn't have this type of data through Planet, I were, being helping them in some of the work that they're doing. And so this is a complete cloud-free products that they have. But we used Landsat at a much coarser, but we used it with the same principle of looking how each single pixel of vegetation indices and crop vigor before the signal saturated at, in the middle of the summer, we detected the spatial variations. And so by using that, we scaled the yield stability maps per field for every single field. They're close to about 8.59 million fields and 80 million acres. So you can physically click on any single field, common land units, and you get the stability map. The stability map, which is again partitioned into high yielding, low yielding, and area then fluctuates. We did a very detailed mass balance of nutrients. And so we learned that the amount of fertilizer not taken up by the plants, what ends up, it matches very closely what USGS has been estimating on, 1.4 teragrams of nitrogen unused to the Gulf of Mexico, the $700 million of US dollars, per year that is not used by the crops. So farmers basically spend money without getting a return on investment. The 1 billion gigajoule of energy lost and additional CO2 lost from the production of fertilizer. We also learned what part of the fields in this, because we have digital elevation models across the whole areas here, we know the areas where they are more affected by water deficit versus excess water. So if you see this next slide, first of all, the separation, let's say in the case of Kansas, this is just for corn, but there are about 1 million acres, 2.2 for what we detected, 2.2 million or so, and 59% are constantly high productivity. That's a very high because it's mostly, I guess, irrigated, but 29% of these areas are below the mean of the field, and so constantly underperforming. And 12% fluctuates very low, again, potentially because of the, the risk elimination through irrigation. 12% is unstable, which 50% of the time it's high yielding and 43% is low yielding. But if you look at the case, for example, Illinois, of the 23% of unstable yield crop, 64% high yielding and 36% of the time low yielding, because it's mostly basically either not enough water. Whenever they go on the other end, it's mostly too much water in depressions. And so topographic features play a big role in the unstable, in addition to weather. And it's important to understand that this type of variability that we're talking about, even though soils play a critical role, but if the variability was only driven by soils, those maps will not fluctuate like that, because the soil wouldn't change from one year to the next. So why are we having such a big, sets of colors that fluctuate? Because it's the interaction between the climate, the position in the landscape, even management if plants don't emerge, and heterogeneity of the stands and so on. And then further, just to tell you how much we know about these fields, what percent of the field is in a depression, what percent is hilltop, what percent is slope. And so this, my lab is really the only one that capture this, even when we do crop modeling. Most of the times they basically assume, uniform, flat areas. And the other important thing is, I guess you may know this, but it was surprising to me about the sizes that basically, in Kansas, 42% of the field sizes varies between 15 and 45 hectares, so multiplied by 2.2. But you have a big chunk of the fields that don't go much, they're basically between 15 and 40 hectares. And so the sizes are not as huge as you would necessarily expect. And so the low yielding areas across this, we also know a lot how contiguous they are. So they are, for the data set we use, that 23 million acres of low productivity. Now, 15.5 million acres are in the middle of the field. And you will know, I guess you will accept that fields have been joined and you can clearly see where the fence lines were or where animals were. So there is compaction or changes within, in the middle of the field. But also in the past, fields were always had a grass waterways. Now we grow corn as a result of the way insurance is given, multiplied by the number of acres. It's paid on acreage. And so now corn grows pretty much all the way to the asphalt of the road. And so 7.5 million acres are on the edge of the field. And now, again, on this 23 million acres analysis, you can sequester up to, on average, about 1 ton per 23. So 23 million of CO2 equivalent greenhouse gas emissions. Just by managing this, you can pull, so 5 ppm of CO2 per year and reducing nitrate leaching, because what you see, this 25% of the land causes 80% or 75% of the pollution that occurs. The high yielding areas do not lose much nitrogen. They basically, it's used by the crop. The crop needs it and it takes it up. So now the same concept we used as a profit stability. When you stack all those years together, the question of farmers is the same areas of the field giving me the same amount of money? It changes, and so we adjust the price. We did a proper analysis, and so this is an example. If you just pick 1 year and you have corn in 2016 versus the one on the right is the conversion. But when you have out of 11 years of yield maps and you do the analysis on the 7 years of corn, then you'll see a lot of the reds loses about $200 per acre. And this is basically real data from several farmers integrated here. So you'll see the stability zones on the left, the fraction of each of the zones. And so the first field, unstable zone, 16 acres. The yield was 134 bushels. Well, you need close to 170 bushel to break even. So basically doing all the detailed analysis, everything, these are data that were shared by the farmers. They lose $40 an acre. The next, the low and stable, loses $63 an acre. But they do make money on $100 on the 56 and 23 high and stable. Now the next field, I had to remove the names, but the next field loses up to 139. The next one, 166. And the high and stable zones of the third field only makes $1. And obviously, as you know, if they go through the insurance and the actual production history, they have a buffer that for $8 an acre, they have insured for the actual production, which can be 160, 170 bushels. So these are numbers that farmers couldn't believe it. And that's doing their own analysis. And so are we serious about this? I mean, are we really, farmers are losing money by putting things that we're saying agriculture creates pollution on these areas? And pretty much everybody agrees that, that part shouldn't be even grown. That field should be changed, but they just don't do that. They don't change. They don't go to the next. And so I have pages of this that it's all red, and only the high and stable zones basically generate, which are also, as you've seen, the close to 50% of the part of the fields. But the other 50% of the field has almost same chances of losing money. And so I was invited to have this view in Nature Food about, starting with this terminology that's been around, but how can we do this digital precision conservation? So you go from the profitability maps, and you'd say, okay, yes, there are high and stable areas that we know through, again, the digital twins and the possibility of observing through images and see how high and stable through the stability map, where you will get a response, a high ROI, a return on investment. But on the other parts, you can basically plant to increase ecosystem services, so increase biodiversity. You'll see there are pollinators or CRP mixes on within field, and there are large enough areas, and so you can basically, the farmers can start avoiding emissions, sequestering carbon to perennials, and start making money off of those areas rather than seeing pollution as well as basically losing money. And so this is modeling across low productivity areas and the amount of carbon they can store through the perennial systems. And so we now give what we call biodiversity conservation areas. Instead of giving the rest of the field will have a VRN. So now we offer these two type of approaches, the BCAs, biodiversity conservation areas, where farmers, this is an NRCS grant, is a $4 million grant that I received by basically paying a big chunk of the money goes to the farmers to be able to say, if you remove these low productivity areas and you sign this contract, it's an official contract with Michigan State, they get paid the price of the rent. And so Joe says, this is like having barbecue with no bones. And the ones that they've been exposed, they love it. They say, this is incredible. This is the way to do it. We love hearing the birds and all the good things. But I can't give enough webinars or writing papers. It's just hard for the majority of the farmers to basically start changing. And the technology is publicly available, free to basically continue to do this analysis. So that's an example. That's a glamorous shot from a drone of an areas that was basically not good areas. And now there are, the mixes. We use this geospatial, I won't go much in details, but crop models, digital twins sit in the middle. You have imagery from different sources, ground truth measurements. And one important thing is that when we run models, we always keep in mind the trade-offs. What is the marginal value of one additional kgs or pound per acre of nitrogen? Does it return money on investment? And so the first one's big jump, the second, in terms of different rates. And so you can model those rates and be able to get this trade-off analysis per zones by not having just profitability, but also environmental impact. And so what is the rate that gives me the highest yield without going into the next level of, incrementing nitrate leaching? Then we have prescription map that you'll see the next phase, and they go directly into the farmers. We've been able to scale them across large areas. And so this is an example of what the farmers, last year we sent 25,000 acres of prescription maps to farmers, and we never met. And so they were progressive farmers, very tax heavy. And so you can see how pretty precise the boxes are the one we call the St. Thomas boxes. I need to see, the farmers wants to see the results of the comparison, the business as usual compared to the rates that we're putting. And so now you'll see the dots in blue, they're very precise. They stay within the block. And then these are very large boxes, 130 feet, all the rows. And so really large areas that they can see rather than strips. They are within the zones. And so you'll see that this is the one on the left is basically the prescription maps, the RX map, and the one on the right is the yield map. And so you can see the area, I don't know if you see my cursor, but these red dots next to the yellow dots, and they're different, 20 kgs versus 50 kgs pounds per acre, they ended up giving the same yield. So the green areas here that they had the blue, which was lower, still gave a good yield so the inherent variability and the yield stability predominates. And so this is again an example of the imagery and then the prescription, the RX. And then what do you see here? You have low and stable zones in comparison between uniform and variable rate. And the low and stable zones, the variable rate gave the same yield of the nitrogen use efficiency, which became much higher because we provided significantly less amount of nitrogen without affecting the yield. And so in one of the grants that I have on the climate smart commodity is, you go from the yield stability to the prescriptions, and mine is much more on avoided emissions. So scope 3 emissions that the food companies are interested in. And so the avoided emissions basically are converted per field on the areas that they can pay a premium because the grains obtained from a certain number of acres within this field was produced with a reduced amount of greenhouse gas emissions from N2O because of improved nutrient management. And so you can click, these are the fields we work with. You can click here, this is an RX map. This is another RX map. Now, to finish, I published this paper as, Chuck mentioned in PNAS and others in Egg System, and how do we go from linear to circular? And I know it's difficult to read, but just briefly, you can see the drawing basically, be able to do precision conservation, be able to generate energy on the farm, rotational grazing, capturing, drainage, reutilizing, spoon feeding, the crops, and accounting the system feedback of water, carbon, and nitrogen, and potentially all the way to generating energy through renewable. So an indirect way of electrifying or becoming neutral in the Oberbosch in the generation of fertilizer, in addition to some of the microbial, new molecules that they are, coming to be able to provide at least a chunk of the nitrogen with no emissions. And in the end, this was another invited paper that I was asked to write, and how all these pieces come together. We got the big data, sensors, robotics, AI, and models, but also techno-economic analysis and profit. You have to have farm level tools that they're scalable. And so the yield stability map, the possibility of tracking and certifying where the grains come from and how it was managed. But in the end, if you put profitability and you decide on policy, is this area responding to water and nitrogen, and the others is, can we get money from ecosystem services, whether it's carbon, credits, or scope 3 emissions, avoided emissions, or anything through, practice adoptions and so on. But then linking the landscape analysis tool as trade-off between energy, water, and profitability, scaling to eventually lead to proper policy analysis, working closely with the government to be able to design potential, again, incentives. Coming here, I was at the food system and meetings at FAO. The European Union is much more, with using sticks rather than carrots. We can do the incentives for proper, ecosystem services and still get, a significant amount of the co-benefits, because the complexity of agriculture is it takes time to be able to see. And so policy are the primer and very much needed to be able to see this change. So with that, I stop, and I thank you very much indeed for your attention. There's some, the people in the lab, and thank the, obviously, the funding agency. Otherwise, this work wouldn't be possible. Thank you.
Okay, thanks, Bruno. I always like to hear his presentations. Transformational change and thinking. So again, I wanted to have him present, so that would help stimulate our discussion tomorrow in the breakout. But now's the time. We got time. It's not too late in somewhere in Italy.
It's okay, I'm in Rome, but I can certainly spare another 15-20 minutes.
Okay, all right. Well, thanks, Bruno. You can have a glass of wine for us. And we'll have
wine. I didn't have it beforehand.
So, okay, questions for Bruno? So Bruno, on the you had years of data stability, but I guess with changing climate and we're seeing more weather extremes. And I certainly in this part of the country, we're seeing that weather variability. How do you think your analysis will change if we get more, droughts or wet periods, even within the same year?
So that's a very good question, and we actually working on this in addition to recommending a paper that deals how the unstable zones are basically determined and what's affecting them. As I mentioned, Chuck, a big role is by precipitation and position in the landscape. Now, temperature obviously would affect the crop development and be able to pull out water and so on. So what we do in this case, you can imagine that we use stability maps by removing, for example, all the wet years or removing the dry years and keeping and see how much they change, right? Now, what we do to forecast and be able to see, we have the only other tools because we don't have the observational data, we run the models. So because the model has been, when we run a model, now they are parameterized by stability zones. So there is a paper actually that I have, PLOS one, where we took all the water for 3 weeks that was measured, that occur over Michigan, and we put it all the way to the 22nd day. And we compared the response, so basically a drought and a deluge, like you remove 3 weeks with no rain, and then you put it all the way at the 3rd week. And so we compared what system would cope better, is a conventional till or no till, and obviously it just showed how much of a yield reduction you will get. So it's very much, but you have no other ways of doing this analysis by running models and imposing extreme weather event. Because, as you know, the KBS site for both LTAR and LTER, which I'm a co-PI on both, we have this rainout shelter everywhere. I mean, they're like 50 now or so. And so we are basically accounting for this. But every year it takes time. So I can run the experiments with a significant amount of manipulation and see if the field become all unstable. If it becomes all unstable, they basically go from being really good. Now all of a sudden it goes down. The farmers needs help in managing the, basically in season. So instead of being much more strategic, pre-season kind of settings and knowing the areas that they're always good and saying, I'm going to go safe here. Now he or she doesn't even know because they're changing. And so you have to have more of a tactical in season, which means more imagery analysis and more this dynamic. And so the technology is working all towards it. It's more how we educate, the farmers, to do this implementation. But in terms of research, we're accounting to see, and unfortunately, the prediction are not very good because between the field because of topographic features, like you said, the same thing that we observed during the same year, one part is stunted for too much water, a depression, and another part is dry. Basically ran out of water because the hilltop, it just, ran off and it went there. So, and those are the things that spatial management will become the way to really be able to do that. One size fits all, it will not be able to continue to be efficient, in the past. It never will. It was always overestimating in some part. And so that's how we account for linking to projection and seasonal forecast.
Another question is, far as soil management, is there ways that we can reduce that or mitigate that variability? And I remember Jerry in 2012, anecdotally, there was that the no-till fields in Iowa had less. I mean, they had a yield reduction, but they were only 40% yield reduction, where the Iowa claimed they had a drought, but they didn't know what a real drought looks like. But then they had, if I remember right, 60 or 70% yield reduction in 2012 or that time period. So are there, and one of my students, Carlos here, is we haven't seen a yield benefit, but well, in some cases we have, but what he did was measure yield variability across this is Justin's place, and the yield variability across that 20-acre strip or whatever was greatly reduced. So are there things that, regenerative ag, between increasing organic matter, building soil structure, whatever, regenerative ag, climate smart ag, whatever you want to call it, that we can do to help reduce that?
So I'm familiar with, I work so closely with Jerry that, Jerry had water table, though. It wasn't necessarily management. He had at 1 meter. And so the plants, because of a little bit of a drought, it was a gift. They reached the water table at 1.2 meter. Wow. And so we ran models and we compared different models on that data set. And so basically we learned about that he had like less than 100 millimeters of rain in the season, but the yield were 10 tons, which is nearly impossible. So plant were taking water. The regenerative agriculture, you mentioned all the things. Chuck, the most difficult thing is to allow farmers to understand that it takes time to build soil and they need to stick with the practice. It is just heartbreaking to see tillage, basically returning to tillage after 4 years, that you basically lose everything that you built. So you mentioned, you build organic matter, you have more stable aggregates, carbon stays inside, holds more water. The other critical aspect is managing residues, basically allow have more infiltration, reduction of evaporation. So there is no more doubt on the co-benefits of using regenerative and whatever terminology people saying, but this is really, in addition to be conservation agriculture, this is trying to revert the trend, but it also includes rotations, which we don't do enough. And so we have, the tier system that are always, you get the minimum amount and then you do cover crops, but some may even, continue to do some of the tillage. But if you start doing no-till cover crops and you change rotation and you have buffer of alternative, it takes time to build this system. And that's why the government needs to understand that any money that goes into this is significantly less of the damage that they will have to pay the farmers when they get really heavy consequences. So that's the mentality that we have all to kind of, first of all, we have the science needs to be joined much more on the message and not basically shooting on each other on messages that divert, unless it's really supported by, strong evidence. But the incentives, unfortunately, the market is the other way, because one is the policy. The other one is if now I don't want to say, you need, but if someone continues to, heavy tillage and heavy fertilizer and all the other things they're polluting, that food produced should cost basically more, because the cost, it should be the other way around, that now we say, oh, the consumer should pay for the environment. Actually, the price of the food that is non-environmentally friendly should cost more. People don't buy as much because there is a cost associated with that production. It's a little bit of change of paradigm shift. The one produced efficiently should cost more, so people will be incentivized to buy and get farmers to be paid indirectly. It's not a popular in many farmers, not joining the change, which doesn't fly through them, and that's a problem. But they need to understand that the system takes time to build, and you know that well as a soil scientist. The soil doesn't change in 1 year.
Yeah, thanks. Andreas, and then, okay. Go ahead, Andreas.
I will learn from the higher discussion with the farmers that timing and calendar of operations was one of the most important factors in managing farm. So I wonder how feasible is to implement and manage these highly fragmented biodiversity conservation areas. I wonder, you know, if you guys receive any feedback from the farmers and maybe the question also to the farmers that are in the room, how would they implement that kind of biodiversity?
You have to repeat.
Yeah, no, I'll repeat. So Andreas asked the question, we had a farmer panel a little bit earlier this afternoon. And one of the issues was time. And to get all the operations. So now if you got these fragmented fields, the labor and time issues to manage that, have you thought about that, or your interaction with farmers as far as the effort required, you know, time required to distribute that fragmentation in a field?
Yes.
You go to the cost inside of the field, so you got different crops, but you manage, you know, an island of one crop inside of the bigger crop.
So if you have different cropping systems too, not just nutrients, but cropping systems, and are you planting different crops? What's the time requirement for that?
Yes. Well, I mean, that's a complex, certainly a complex issues, but remember, I don't think we should even consider the opposite solution to say, okay, put fertilizer in the fall, you know, like they do in the 3 ice states, just because so you have much more time to distribute that. The only way in which I don't know if it's the right from an economic point of view is to basically hire, you know, cooperative or subcontractors where you basically go whenever the time is right, which will bring additional work and rural, you know, more rural prosperity in the sense of, you know, paying $8 an acre or whatever per application. It's not that it doesn't cost to the person to do it, but there are no other solution. You only have one machine and it takes the time. It may take a month before you finish, you know, all your large farm. So the thing again, back on the fact that you build your system, you may need, you know, you basically may not need as much, but you would still have to intervene, no question. The models will also help you to say where you should go first in terms of both the planting, you know, should I plant this field? Can I wait, you know, for the other field with different characteristics in soils to be planted later? I fully agree, and that's part of the complexity on be able to manage such a large, you know, such large farms. The other thing, just to say, 67% of the U.S. Land is rented because you make. So it goes back almost to the vicious cycle to say, okay, why do they have to get all this land? Because you have to you have the amortization. One machine, you make more money per acre because you have everything standardized, right? So you grow the system, and any changes that you make, it breaks the system that they have. And so that's where, if there needs to become, it needs to be incentivized to say, listen, in order to do that, you will get this level of support. But otherwise, we are prisoner of the current system, and it will never change if they say, okay, I don't have any other solution. I mean, I don't know if I'm helping the conversation, but we are victim of the current way of the way the system is, you know, these extensive large areas that grow, you know, these crops versus, and I'm not advocating to not use corn, but changing the rotation or putting corn in areas where it's just more productive and less risky to do, it will certainly help in managing the farm, you know, more efficiently. But it is certainly a complex issue.
Paula? Yeah.
I have so a question would be, when you're comparing the stable or the stable system, you're comparing just the grain mill, you're not taking into consideration the cost of production or the cost of when you or the grain or like the market price.
Yeah.
So how would you
Yeah, so I think I can answer, but I'll let Bruno answer. So The question was, are you only comparing stability as far as grain yield and not the cost of production practice, inputs on the stable and unstable zones?
No, I mean, it's a full balance of everything.
Yeah, so Bruno considers the cost of the nitrogen, putting it on, making the fertilizer, as well as the yield and output cost. So it is a complete,
Total complete analysis.
what, Paul?
And the price when we sell also.
Well, what about variability in price?
It's accounted, that particular data set was the price, how much he paid and how much he sold the grain. Now, when we don't have that, we still have a model, you can go back and find out what the price of urea was in 2021. So it's adjusted by the year as well. We can't do for the future, but the past the price is known.
Okay.
I think this is really interesting. What is the vehicle you see for getting these prescriptions from your lab or wherever to the farmer? Because they're not going to have the time to go every field. This prescription here, blah, blah, blah.
Okay, so the question is, how do you, Bruno, you get your prescriptions from your lab to the farmer? Because the farmer's not going to have the ability to do that. So how do you?
Yeah.
So
that's
that information.
Yeah, exactly. And we're not a company and we offer them completely for free. The ones that we send, these 25,000 acres, are part of this NRCS grant. So they basically, they even get, I mentioned paying for, the biodiversity areas. The one that implement nitrogen, they get $10 an acre from the project. And so it's the other way around. We pay them in order to get the as applied maps back to us. So we open this call to different farmers group, and they joined. Now on a one-to-one basis, we don't offer a service. It's something that eventually could happen in exchange of, again, the possibility of maintaining a system or but it needs, support. And so as long as we have that support for the next 2 years, we welcome as many, because the technology is completely scalable. So Chuck, through, the person that asked the question, if they say, hey, we have 2,000 acres, we'd like to have a prescription, all I need to have is basically the coordinates, we'll get the stability maps, the weather, the soil, and then the management will interact both with the person and as well as with the farmers, run the model and send the prescription that goes directly onto the, the ISO bus on the machine, and it gets implemented. But we're still research lab.
Yeah, so I guess in the future to scale up, then
a company
then that'd be a company or consultant.
Yeah, a company that wants to use exactly, and the algorithms and the things are all published. So they haven't I mean, one reason, I know you may have people from the big ag in the rooms or in general, it's just always hard to think that someone will advocate a reduction of inputs. Both the seed companies never want to risk the performance of the seeds by not putting enough, fertilizer, and the ones that sell the agrochemicals are not necessarily in favor of reducing that. So there is a complexity, even that they have their own algorithm to do it, and they give the prescription to the farmers. But until I start popularizing this approach, the low yielding areas, Chuck, will receive a greater amount of N. And I've been basically showing them, but if for the last 10 years, your yield has always been 120 bushels and you manage that area with 200 pounds of N, doesn't that tell you that nitrogen was not the issue? Because you've been putting sufficient amount of nitrogen and you get much less yield compared to an area where you put 200 and you got, basically 220 bushels. And so that means But before a farmer goes and says, you can only put 70 pounds or 80 pounds of N, it takes a change. It takes, they're very not, in favor. But once they see this, then they realize, and I say, why am I putting these fertilizers basically to the water rather than to the plant?
Okay, I'll get a couple more questions and then we probably should end, but Carlos.
It's kind of related question, so 30 years in conservation and probably good management techniques to identify marginal areas that it should go to conservation. So what is the rationale behind what areas should I really give up and keep it in as conservation for the areas that I could do something to maybe make those areas possible? So how do I, what's the practical for that?
I'll see if I can paraphrase that. So your conservation mapping, precision conservation mapping, there are areas that are low yielding and maybe shouldn't be farmed in that. So I guess, so what is your threshold to decide if it should be put into corn or put into grass or for biofuels or something? What's your
So excellent. We did the analysis.
Hang on, Brendan. What?
And what are the areas that I can maybe do something to improve over time?
Okay.
And make that up.
Okay. Yeah. So to add on to that, so what's your threshold, and then what's the possibility for making those areas? Say if there was grass for 10 years and now you made it more productive, increase organic matter.
Yes, yes. So the first question was almost chosen with the farmers. They say, what would it take for you to just drop? If you know you're losing money, what would be that amount that it will get your attention? And believe it or not, they said $15 per acre. If they lose $15 per acre, they basically will do something about it. And so the threshold was 15 below goes to BCA. The problem was never 15, it was $200, $150, as you've seen, the numbers. Those, the numbers is nothing, it's all observation from inputs and output. All the expenses, not just fix everything, fixed and variable cost, insurance, everything. And so basically was it profit, okay, economics. It was what drove. And then yes, could you go back? There is a question there. What drove that field to go this low, and now you're bringing it back? The question is, do we need the grains from those areas, or could we still live with the ecosystem services off of those areas? You see what I mean? Is really what is needed. If some of the grains goes for feeds and some for biofuels, could we find the simple answer to that? I wouldn't necessarily go back to corn, because you can cut the prairies and put it for energy, and that will have zero nitrogen input. If you go back to corn, that will start, in order to have, yes, you have better organic matter, but you will still have to include more inputs, and the cost goes back. So there is just a more efficient way of these areas to stay potentially as long as it is possible to keep them under conservation for ecosystem services.
Okay. So Anna, you got the last question.
That's good. My question is, once you make the decision of having those areas that you're gonna not give up, but allocate for ecosystem service, is that like a permanent thing? And like, if not, how would we know if we could back to make that area agriculture again? Like, is that like a decision that we're gonna, stick to it for the rest of the journey?
Yeah, so somewhat related question that was asked, but when you allocate that land to be for ecosystem services, is that a permanent thing, or can you make a decision to take that land back out of production? And I guess this related to this conversation you and I have had about CRP and putting payments for CRP to keep it in wildlife habitat.
Well, again, the question is if we still continue to prioritize economics over what is happening to the climate, the reconversion back to a potential production immediately leads to emissions, because you have to put nitrogen and you have to somehow till to be able to get, the crops back in. And so you lose immediately, one tillage event loses close to 6 to 7 years of carbon. That we've been showing that over at the LTER. So it's back, or is the person so much in needing of doing, you have to do an analysis, is this reconversion to corn, is the price of corn to a level that has basically happened in some cases where some of the CRP was converted into corn for 1 year, and then the price dropped down, and then we created more basically environmental impact. So the question to me is, good land should be used for production and incentivize, sustainably intensify. So basically, potentially, it's a paradox. You should be putting more nitrogen in areas where you have, a meter deep soil that stores water, and you get 300 bushels where it's possible. They're trying to get 100 bushels from an area that is so risky and the emissions is greater than the storage.
Let's just take Oklahoma out of production. No, I'm working on a potential project where we're looking at incentivizing keeping CRP in CRP.
Excellent.
We're still waiting on that funding, Bruno. But the idea is, this case is Nature Conservancy, can they incentivize and maybe even put fences up, help put fences up, then it can be grazed, but still keep the carbon in the soil and keep it grazed and still provide wildlife habitat. So there's still some outside income as well as inside income from grazing and feed.
Exactly.
So
I heard that farmers are making significant amount of income from agrotourism, like for hunting or for renting. Then
yes,
that's the diversifying source of income. We have to get away from the mentality that the only way to make money, which we've shown that they are not making money in those areas, is to continue to grow the same crop that they grow in a good land, on the good areas.
Yeah.
That's a little change, a paradigm shift that is needed.
All right. Well, thanks, Bruno, for staying up late. Maybe you are a late night owl, so maybe you can go out and party.
No,
but I really appreciate
I get up early in the morning as well. So
okay. Well, yeah, I appreciate it. Well, the Italians, they eat late anyway, right?
say hello to Jim. Hello, Jim.
Yeah.
Good to see you.
Yeah, thanks a lot, Bruno. And hopefully it'll stimulate thought for our discussion tomorrow. So
Yeah, I
really
wish you the
appreciate your
best with your project.
Okay, thanks, Bruno. We'll talk later.
Very welcome.
Okay.
So long. Bye.
Hi, Jam. You're muted.
As usual, I'm muted. So excellent day, Chuck. It's been
All
really
right,
great.
thanks. Well, we're gonna have a poster session and cash bar. So send me your cash
good.
and we'll drink for you.
Okay, that sounds like a good idea.
Okay,
I'll see you tomorrow morning.
see you tomorrow morning. Thanks a lot,
Okay.
Jim. Take care.
Bye-bye.
Okay, the posters are